All right. Right. Good evening. We'll start. I hope I'm clearly audible and I'm visible. Right. So today it's actually a continuation of where we stopped yesterday. Right. Yesterday I had the session 21 of S2A and that was on the Western Provincial paper discussion. Right. Sound is fine, right? Okay. It was on the Western Provincial paper discussion and today I'm doing the continuation of that discussion we did last day. Right. So I hope all of you have got the paper, right? Got the paper yesterday, right? If you haven't got the paper, right? If you haven't got the paper, uh, it is not pinned here today, right? It is not pinned here today. So what you can do is, if you haven't got the paper, you can go to the previous video, right? And go to the chat of the previous video, and there's a pinned comment, right? From that pinned comment or the pinned message, right? You can get it. You can get it if you haven't got it yet. Okay, then let me share my screen without further ado. All right. So I think the screen is visible. Right, I think the screen is visible. Right. Let's start. Okay, so we stopped at 25th question yesterday. Right now we are starting from 26. Right, 26. A uniform rod of length L has a mass M. Mass M. The rod is kept horizontally and rotated about a fixed axis, passing through one of its ends at a constant angular velocity omega naught. Okay. Then it is like this. Rod is connected, right? And it rotates around one of the ends, passing through. A bead of mass simple M is placed on the rod near the axis of rotation and can slide smoothly along the rod. Right. So there's a bead initially here can slide along the rod. When the bead reaches the midpoint of the rod, the angular velocity of the system is. Now, when this reaches the midpoint, when this reaches the midpoint, if the length is L, right? Now, this is when this has reached a distance L over 2, right? L over 2. Then, omega of the system. Okay, if there's no any external unbalanced torque acting in the system, right? We know angular momentum is conserved, right? Angular momentum is conserved. Then I1 omega 1 equals I2 omega 2. Angular momentum is conserved initially. Initial angular momentum, right? I1 1 over 3 ml squared. Initial omega is omega naught. And there's no angular momentum for the bead because, right? There's no angular momentum for the bead because that is at the axis. That is at the axis. Then, secondly, 1 over 3 ml squared is for the rod, say omega dash, plus this is for the bead. Bead rotates about an external axis, right? For external axis, we can write moment of inertia always as mr squared, just mr squared. Then mass of the bead is given as simple m. Then mr squared. Now r is L over 2 squared omega dash. Right. Then simplify this. Simplify 1 over 3 ml squared omega naught equals for this side omega dash is common, take it out, right? Omega dash is common and take it out. Then this is ml squared over 3 and here this is simple m l squared over 4, right? Now you can see L squared is also common. L squared is also common. Then L squared cancels. Right? Now, both 3 and 4 are there here. Right? Both 3 and 4 are here. Since both 3 and 4 are here, right? Then what if we multiply this by 12 or else by the common denominator here, right? Common denominator issue right? That's also fine. That's also fine. Then let's simplify this way. Now this is m omega naught over 3, right? And this is omega dash, right? Omega dash capital M over 3 plus simple M over 4, right? Then to subject omega dash, let's multiply everything by, the common denominator 12. Then this becomes 4 capital M omega naught, right? Omega dash, right? 12 here means 4 capital M. 4 capital M plus 12 means 3 simple M, right? One more second. One more second. There's a small mistake in the question. Yeah. There's a small mistake in the question. Let's do this way. Moment of inertia around the axis here for rod is not 1 over 3. That should be 1 over 12, right? Let's do that correction. Otherwise, it won't come, right? This is a correction we have to make, right? This should be corrected as 1 over 12, right? This should be corrected as 1 over 12. Listen. That's a typo, right? That's a typo I didn't notice at the beginning, right? This should be corrected as 1 over 12, right? 1 over 12, right? Correct it as 1 over 12. Then if there is 1 over 12, right? Now let's see, right? This must be corrected as 1 over 12. I'm doing these corrections. 12. This is 1 over 12, right? 1 over 12, right? Then this is 12 now, right? There is 12, right? Then we'll simplify this point onwards now, right? See, okay. Around the middle axis, there is actually 1 over 3, right? Now that's an index is given, no? 1 over 12. All right. Then simplify. Then this is m omega squared over 12. Then the other side we have omega dash, then m over 12. And this is simple m over 4. All right. Multiply the entire equation by 12. Then m omega squared equals omega dash. Here capital M remains. By 12 means here 3m. Okay, now it's done. Then omega dash equals m omega naught over capital M plus 3m, right? This is the expected answer. That is 1, right? That is 1. Please make that correction. It should be corrected as 1 over 12, right? Moment of inertia should be corrected as 1 over 12. Then 27. Radioactive substance has a half-life of 30 minutes. The percentage of radioactive substance remaining after 2 hours is, right? So we know N equals NO over 2 to the power NO, where N is number of half-lives. N is number of half-lives, right? Then N equals, right, NO 2 to the power N, 30 minutes, 2 hours means 4 half-lives are passed, right? 4 half-lives are passed. Then remaining part as a ratio is N to NO. NO is original number of nuclei. Then 1 over 2 to the power 4. 2 to the power 4 is 16, no? Right? 2 to the power 4 is 16. Then the ratio is asked, percentage is asked. Then percentage of this 100 over 16, that is 6.25. That is 6.25. Right? That's an easy one. 6.25. Right? 28. . 28. A pile hammer of mass 5m falls from rest through a height touch into a pile of mass 20m. If the impact is perfectly inelastic, the percentage of energy lost in a single collision is right. Then, if it falls for a height touch, we know, right? We know after falling a height touch, the speed or the velocity that it is going to get is given by root 2gh. No? The speed is going to give by root 2gh, right? Starts from rest. Right now to find the velocity, if there is perfectly inelastic, which means after the collision, these two are going to merge together, right? Perfectly inelastic means now after the collision, these two are going to combine together. Then for that combination, for that merging, we can apply linear momentum using linear momentum. Right? Now initially, masses are given 5m, this one is 5m, and this is going to collide with a 20m. Right, then initially 5m travels with this velocity root 2gh, right? And 20 is at rest. And finally, total mass is 25m. Let's say their velocity is u. Then m cancels, right? And u is root 2gh over 5, no? Root 2gh over 5, right? Now the question is about percentage energy loss. Right? Percentage energy loss. Then delta E over E1, no? Percentage energy loss. Then in terms of kinetic energy, if we write this, now final kinetic energy, initial kinetic energy was half m, right? Half m cancels actually. Half m means initially 5m, right? V squared is 2gh, no? 2gh minus final energy half mass is 25m, and its energy, right? Its energy is 2gh over 25, no? 2gh over 25. Whole thing over initial energy again half 5m 2gh, right? Then half cancels, m cancels, right? Now here this 25 to 25 cancels, no? Right. Then simplify the remainings. Right here, 5 times 2gh remains. Can you see 2gh is also common? Then cancel the 2gh. Then here 5 minus 1 remains, and below 5 remains. Right? Now this number is 4 over 5. Then we need the percentage into 100%. Right? That is 80%. 80% of energy is lost. That's a different aspect, different perspective of loss of energy questions, right? A different perspective of loss of energy questions, right? 80% loss is 80%, right? A little bit different idea. 29. A total charge Q is uniformly distributed throughout the volume of an insulating sphere of radius A, which graph correctly represents the variation of electric field intensity with distance measured from the center of the sphere, right? Now this is something we prove in Gauss theorem. Right? For an insulator sphere, right, it is non-zero inside also, right? So the variation we get is something like this, right? Variation we get is something like this, right? Then only this side is given, it is 5, right? Only that side is given, that is 5. 30. The voltage gain of the operational amplifier circuit shown here is, this is the standard non-inverting op amp, no? This is the standard non-inverting op amp. standard non-inverting. Then we know V out of V in is given by 1 plus R1 over R2. 1 plus R1 over R2. Right, then 1 plus R1 is also R, R2 is also R, then this is 2. Right, that is 2. That's a simple one. 31. 31. An object of mass simple m suspended by a string of length L from a fixed point O is made to move in a horizontal circular path such that the string makes an angle theta with the vertical. Right, as shown, if air resistance is negligible and the angle theta remains constant, the period of revolution of the system is okay. Now if I mark the forces here, right, see, say this is t, then this angle is theta, we know, then this is t cos theta, no? And here mg, and towards this direction you have t sin theta. Right, now in a circular motion, right, for a circular motion what we do is applying f equals ma towards center and taking a vertical equilibrium, no, because that's a horizontal circle. Then first on vertical equilibrium, vertically upwards we have t cos theta, vertically downwards mg, right, mg, and then can use f equals ma towards center, and let's say this radius is r, now from the diagram I can see sin theta is given by simple r over l. From the diagram sin theta is r over l. Right, then f equals ma towards center, f equals ma towards center, right, f equals ma towards center. Then only force which acts towards center is t sin theta, right, that is mr omega square. Then say this is equation 1, this is equation 2, right, divide these two, then t cancels and sin theta over cos theta comes, sin theta over cos theta, right, m cancels, then here r omega squared over g comes, r omega squared over g comes. Now for r, I can see from here L sin theta is applicable. Then this is sin theta over cos theta equals r is from that equation, r is L sin theta, omega squared over g. Now sin theta cancels off, right? Then subject omega squared is g over L cos theta, Then omega is root g over L cos theta. So we all know that omega equals 2 phi over t. We need period 2 phi over t. Then t is given by 2 phi over omega. Right? T is given by 2 phi over omega. Then t equals 2 phi over omega. Right? That is 2 phi over omega means reciprocal value. Then L cos theta over g. 2 phi L cos theta over g is 4. Right? So kind of a different and a beautiful question. Then 32. Right. Now, if this is the direction of E, we know the component acts in this direction of E is E cos 30. Right. So with that, if we go to the question 32, a uniform electric field of magnitude 100 VA minus 1 acts in a perpendicular direction, acts in a direction inclined 30 to the horizontal as shown. If VA and VB are the electric potentials at points A and B respectively, then VA minus VB is. Okay, then along this direction, right, I'm going to use E equals delta V over D, right? And about electric field lines and the direction of electric field line, we know that is always from plus to minus. Direction of electric field line is always from plus to minus, right? Direction of electric field line is always from plus to minus, right? Then since the direction is from here to here, right, definitely A is positive, right? Definitely A is positive. Then I can say positive in the sense VA is greater than VB, then I can say, right, VAB is a positive value, VA minus VB is a positive value, VAB is a positive value. Then remove all the negative answers, right? We'll see. Then E here is E cos 30, right? E is given as 100, right? Cos 30, root 3 over 2, right? E root 3 over 2. And delta V is, right? Delta V is what we need. And the distance is 20 centimeters, no? 20 into the minus 2, right? Then this 2 cancels. Then delta V equals, this is 10 to the minus 1. Then 10 remains, 10 root 3. Now I found before that it is a positive value. So that is positive 10 root 3, right? That is positive 10 root 3, right? Because we knew that V is greater than VB. 33. A long wire of infinite length with non-touching conducting sections is bent at region A as shown. If the radius of the circular part is R and the current flowing through the wire is I, the magnitude and the direction of the magnetic flux density at the center is. Okay. Then first apply the right hand rule and check the directions. Right. First apply the right hand rule and check the directions. From the linear part at toe, right? Apply the rule and see. From the linear part, when current flows downwards, that is upwards, right? And upwards means that is outwards, actually, not upwards, that is outwards. And from the circular part, that is also outwards. Then they are going to add up. Then B equals mu naught over 4 5, right? From a linear conductor, we know this is written as 2I over R, then 2I over R. And from a circular conductor, that is written as I theta over R. Theta here is 2 phi over R, right? Now, 2I over R is common, right? Take it out. Then mu naught over 4 5. 2I over R is common. Then 1 plus 5 remains inside. 1 plus 5 remains inside. 2, this cancels 2. Right, then mu naught I over R, mu naught I over 2R, keep it here and multiply the bracket by 5. Then this becomes 1 over 5 and this becomes 1. Then mu naught I over 2R, 1 over 5 plus 1, right? And that is outwards. This goes out, there is dot, right? There is dot, outwards. Then 4, right? Out of the paper, 4, right? Thirty-four. An electron and proton with equal linear momenta enter a region containing a uniform magnetic field from a region where there is no magnetic field. Which of the following statement is correct? Okay, then we know, right, when particles enter magnetic fields, right? When particles enter magnetic fields, they travel in circles. The radius of that circle is given by mv over bq. Radius of that circle is given by mv over bq. Right, now check what are the constant values here. The electron and a proton, right, with equal linear momenta. Then mv is equal. Right? mv is equal. Then entering the same magnetic field, B is equal. And about charges, in terms of the charge, electron and proton are equal in magnitude. Right? Everything equal, which means therefore R is equal. Right? Now let's say this is the electron. Right? This is the electron. And say this is the proton. Apply Fleming's left hand rule and check the direction of force here. Right? Check the direction of force here on the electron. If the field is cross, right? When electron travels rightwards, current is opposite, then direction of this motion is something like this. And for the proton, direction of the motion is like this. Right? They are equal circles but opposite directions. Right? Then the electron and proton move in the semicircular paths with equal radii, correct? In opposite directions, then it is 4. Right? It is 4. Magnetic fields. Then 35. A uniform rod PQ is freely hinged at point P on the wall on a vessel containing water. In equilibrium, 3/7 of the rod projects out of the water. the specific gravity of the material of the rod is. What is specific gravity? Specific gravity means specific gravity is relative density. Specific gravity means relative density. Right? Specific gravity means relative density. Specific gravity means relative density. Right? Then, okay. Then for this, let's assume the length of the rod as 7L. Right? Then if there is 7L, 3L is out. No, 3L is out. Right? So at this point, weight acts. Say mg acts at the point where it is divided equally. Then this side must be 3.5. Right? And this is also 3.5 in that regard. And we know upthrust acts at the center of buoyancy. Center of buoyancy is at the middle point of the immersed part. Immersed part. Now immersed part is 4L long. Then this is 2L. 2L. Right? Now about point P, we can write a force movement. About point P, we can write a force movement. About P. Then leftward movement is by U. Right, let's assume this angle as theta for these movements. Then by u perpendicular distance is 2L cos theta, no? Right, 2L cos theta. And rightward movement is by mg perpendicular distance is, right, 3.5L cos theta. Right, now cos theta cancels off, L cancels off. Right, then we know u equals v rho g. Then v immersed, vi rho g, right, and the 2 remains here. And m is, again we know m is v rho, then this is v total, right, and rho of the object g, right, g times 3. Now g cancels, plug other terms. Let's consider cross-sectional area of this rod as A. If there is A, immersed volume can be written as, immersed part is only 4L, no? Then there is 4LA, right? Density of the water, OW, then 2. And here, right, this is not 3, it was 3.5, right? 3.5. Then total length is 7L, A, total volume, rho object, rho, right? 3.5 can be written as 702. No? And now A2, A also cancels, L2, L also cancels. Right, then this side is 8 rho W, and this side is 49/2 rho O. Right, we need rho O over rho W. Rho O over rho W. Rho W is, now 8 times 2 is 16, then 16 over 49, right? 16 over 49, it is 1, right? It is 1. The similar idea has been appeared before also, right, about these suspending rods, or rather the floating rods. Right, 36. A glass vessel of volume 5V and linear expansivity alpha is completely filled with a liquid of volume expansivity gamma. Okay, this completely filled with a liquid of volume expansivity gamma, and expansivity of the metal is alpha. Sorry, glass is alpha. When the temperature of the vessel is increased by theta, the volume of liquid that overflows is V. The relation between alpha and gamma is. Okay, then when this is heated, let's say increase of volume, right? Let's say increase of volume of the glass is, right, that is given by V1. V1 is given as V1 gamma theta. Gamma of the glass is 3 alpha theta. Similarly, delta V of the liquid is same V gamma theta, right? Same V gamma theta. Then volume 5V, right? Then 5V. This is also 5V. Right, then we know always expansivity of a liquid is greater than that of a solid. Right? Expansivity of a liquid is greater than that of a solid. Then delta V liquid minus delta V glass is the spilled out part is the liquid overflows, that is equivalent to V. Then delta VL, right, is 5V gamma theta, no? That is 5V gamma theta. 5V gamma theta minus delta VG is 5 times 3, 15, 15V alpha theta. That is 15V alpha theta equals V. Right, now V cancels off. V cancels off. Right. And now one remains here. Now 5 gamma theta minus 15 alpha theta equals 1. Right. Now alpha is subjected. Alpha is subjected. Then subject alpha, we can write this as 5 gamma theta minus 1 as 15 alpha theta. To subject alpha, divide this by 15 theta. Divide this by 15 theta. Then 5 gamma theta over 15 theta minus this is 1 over 15 theta. Right? 15 theta equals alpha. Then simplify this. Then from here, gamma over 3 remains. Minus from here, 1 over 15 theta remains. That is alpha. Right? So that is given in answer 1. That is given in answer 1. Right? 37. Due to an emergency fire hazard in an industrial hall, a fixed siren emits a sound of frequency 1600. Right? A person hearing the sound runs horizontally away. Right now, a siren is emitting 1600, and a person is running away. With a speed 2 ms minus 1. Right? At the same instant, wind blows towards the industrial hall at a speed of 20. Then there's a wind here at 20. Wind. Right? We know direction of velocity of sound should be towards the observer in order to hear this sound. Say that is V. So that is V. Right? Now, if a wind is given, you have to factor this net impact of the wind into the sound velocity through air and applying the equation. Right? That's the only thing you should know about such questions. Now we know f dash is given by now for this relative velocity is 2 in the opposite direction. Right. See, f dash is given by velocity of sound through air with respect to observer. Right. With respect to observer. Right. Velocity of sound through air with respect to observer. Now velocity of sound through air is now that is not just v, that is v minus 20 with the wind. Right. With respect to observer minus 2 over velocity of sound through air with respect to source. Source is at rest, then v minus 20 into real frequency 1600. Then f dash equals, right, this is 318 and this is 320 times 1600. Then 0 to 0 cancels, right? This is 16 times 2, then 160 times, it is 0.2, right? 0.2. Then 318 means, right, 318 means this is 318 over 2 into 10, right? Then 318 over 2 means 320 means 160, no? Then 159. Then this is 159, then 1590, right? It's 1, right? It's 1. Bernoulli application with a wind, right? If wind is given, factor the resultant impact. If the wind supports, then it is added. If the wind disturbs, it is subtracted. Right? Then 38. The total mass of 10 cookies made during the New Year season was 125 grams. They were placed inside sealed container where the relative humidity was 60%. After a few days, the relative humidity inside the container had decreased to 40% and the total mass of the cookies had increased to 126 grams, which means additional 1 gram of water vapor is absorbed into cookies, no? Right? Additional 1 gram of cookies is absorbed into cookies. right? Additional 1 gram of water vapor is absorbed into Caucase. Assuming the temperature remained constant, right? If the temperature is constant, saturated values are constant, and oil in the Caucase did not absorb water vapor, the mass of water vapor present in the container before placing the Caucase inside was. Okay, so we know Y can be written as M over M naught times 100%, no? Right? So apply this 2 times. Initial case 60. Initially, let's say the mass was M and the saturated required mass for saturation is M naught into 100. This is equation 1, right? And then as a second equation, 40 equals, now 1 gram is lost from the atmosphere, no? Because Caucase has absorbed 1 gram of water vapor. Then from the atmosphere, 1 gram is lost. Then this is M minus 1 over same M naught because temperature is same. That is 2, right? Then divide these two. Divide these two. When it is divided, 100 to 100 cancels, M naught to M naught cancels. Right, 60 over 40 means 3 over 2, no? 3 over 2. Then from here M remains, and from the second equation M minus 1 remains. Simplify, 3M minus 3 equals 2M. Then M equals 3, which means 3 grams. So initially there had been 3 grams. Right? 39. A parallel plate capacitor is charged to a potential difference V. It's then isolated and the separation between its plates is reduced to 1/4 of the original value. The new potential difference between the plates is. Okay, so we know for a capacitor, right, C equals epsilon naught A over D, right? And we know Q equals CV. Then for C, you can write Q over V is epsilon naught A over D, right? Now, remove the constants for these two scenarios. Q is a constant, even though the plates are taken apart, right? Q is same. Epsilon naught is a constant. Same plates, A is a constant. And which means, right, both V and D are at the new denominator, which means they are proportional, V proportional to D. That's enough. V proportional to D. If V is proportional to D, if the gap between plates is reduced to 1 over 4, then so does V reduced by 1 over 4, then V over 4. Don't do it hereafter. V is proportional to D. Right? So easily can approach. 40. The work done during the thermodynamic cyclic process ABCA can approximately be. Okay, now for such cases, first assume this as a triangle and find that value, because we know work is given by, right? Work is given by area of PV. Then W here is the area of V2E means V3V means 2V and P4V means 3V, right? Then this is the value, no? That is 3PV. And the process is clockwise. If the process is clockwise, the sign of the work is plus. If the process is clockwise, sign is plus. And this is for the triangle. Now what is asked is not about the triangle, right? Then we have to find the area of this loop here, no? That is little bit less than 3, no? For the triangle, there is 3PV. But for the loop, it should be less than 3. Right? Then closest number given less than 3 is 11 over 4. Then that's a positive value. Then the approximate answer is 11 over 4 PV. Right? This is for the triangle. This is for the triangle. And for that given curve, it should be less than 3. Right? 11 over 4 is 2.6, around 2.6, no? Right? That's the closest value. So that's a possible value. Then 41. A light ray from large light source on the ground travels upwards, making an angle theta less than 90 with the horizontal if the refractive index decreases gradually with height. Right? Then now if these are the layers, say these are the layers, right? Now refractive index decreases gradually. If it decreases gradually, say we have an initial beam falling here, then decreases gradually means always this goes from dense to rare away from normal. Again here away from normal. Then again here again dense to rare away from normal. See, the bending is going to be something like this. Bending is going to be something like this, right? So if you have just check the bending, that is enough. That is one. Right? If you have just check about the bending, right, that is enough. That is one. Then 42. 42. The far point of a hyperopic far-sighted person's eye is infinity. He uses a reading lens magnifier. A clear enlarged image of a book is seen only when the book is placed between 10 centimeters and 15 centimeters from the lens. The least distance of distinction of the defective eye is. Okay. Then if this is kept between 10 centimeters to 15 centimeters, that is seen, right? Now in such cases, what is done is for the present vision of this defective person, this range is rescaled or that is reimaged. Then we don't know what the closest point that is seen, that is visible to the person. Let's say that is V, and we know the far point, right? He has farsightedness. Farsighted means he can see infinity. Far point is infinity. Now using the lens, this near point of this range is taken to the near point of the person. Far point of the region, the range is taken to the far point of the person, right? So basically, that is what is done. That is what is done. Now 15 is taken to infinity now. Apply an equation and see what's the lens used. 1 OV minus 1 OU equals 1 OF. Now if you can check this as 15, right? That's totally fine. I mean, without applying the equation, right? If you can just check that as 15 because you know it's a farsightedness, right? Give me 1 second. Okay. Right. Right. Then 15 is taken to infinity, right? Object at 15 is taken to infinity. Then image at infinity, object at 15, 1 OF, right? Then it says 1 over infinity is 0, no? Then minus 1 over 15 equals 1 over F. Then F is minus 15, right? That's a convex lens of focal length 15. Convex length of focal length 15. Then for the near point, right? For the near point, right? Apply the same for the near point. 1 over V minus 1 over U equals 1 over F, right? Now objects at 10 should be imaged at V in order to see, no? Objects at 10 should be imaged at V. Then 1 over V minus 1 over 10 equals minus 1 over 15. Right? F is minus, that's a convex lens. Then 1 over V equals, right? When 10 is taken to the other side, it is 3 over 30. And 15 can be written as 2 over 30. Right? Then 1 over V equals 1 over 30. V equals 30. Right? Which means near point of this person is at 30. Near point of the person is at 30. Right? 43. Two cells of negligible internal resistance having voltages V0 and 6 volts. V0 and 6 volts are connected in the circuit shown. Which graph correctly shows the variation of potential at point P, Vp, with VO? Right, let's start when VO is 0. Right, when VO is 0. Right, when VO is 0. Right, there's no battery here then. If VO is 0, there's no battery here. right? VON, okay. Then VO is here. If there's no battery, VO is 0, which means now VP is non-zero, because now in that case current flows in this direction. Current flows in the circuit in this direction from 6 volts. From that 6 volts current flows. Then my first decision here is VP is non-zero. VP is non-zero. And then since when VO increases, right, it is going to reach 6 volts at some point. No? Since that is a special point, right, I'm going to check that point next. That is when VO equals 6 volts. When VO equals 6 volts, right, now this battery produces EMF in this direction, this battery in this direction, then sigma E becomes 0. Then sigma E of the circuit becomes 0. Right, when sigma E is 0, current flow in the circuit is 0. No current flows. No current flows. No current flows. If no current flows, right, these resistors are not functioning, then this is 0, right? This side of the battery is 6 volts, then VP is going to be 6 volts, right? Then one of the main decisions here, right? At that point, VP equals 6 volts, right? I think now we can finalize an answer, right? It is starting as an non-zero value, and VO is 6 volts. When VO is 6 volts, VP is also 6, right? Then when VO is 6, VP is also 6. That's only one answer. There's only one answer in the given list. That is obviously 2. Right? No need to worry. Obviously 2. Right? 44. 44. Right. When calculating a mercury thermometer, 0 and 100 marks are incorrectly placed at the true temperatures -1 and 101. Right? At the true temperatures -1 and 101. Right? Then for this, have a scale, right? And one side we'll be writing the defective one, the other side the accurate one, right? Defective one and the accurate one. Then in the defective one, 0 and 100 are marked. In the defective one, 0 and 100 are marked, but the actual values of these points are 101 and -1, right? When the thermometer reads 50, the true temperature, then this reads 50, true is here, right? Easiest type of questions we have in thermal, right? Easiest type of questions we have in thermal, write this ratio, right? Write this ratio. Then 100 minus 0 over 50 minus 0. From the other side, 101 minus -1, right? This is theta minus -1. Theta minus -1, right? Then 100 over 50 is 2. 100 over 50 is 2. And this is 102. Theta plus 1. Theta plus 1. Then 2 times 51 here. 2 times 51 here. Then theta plus 1 equals 51. Theta equals 50. Right? So it is exactly reading 50. Right? Exactly reading 50. That is 50. Right? There's only one point these two temperatures are coincided. Right? In this thermometer, that has been 50. In this thermometer. Right? There's only one point in a thermometer when it is defective that is going to be coincided with the other one. Right? In this one, that is 50. 45. 3-point charges plus 5 coulombs each are placed at distances 1 centimeter, 3 and 5 from point O. Right? Then if this is point O, right, these charges are placed, right, 1 centimeter, 3 centimeters and 5 centimeters away. Right? And they are 5 coulombs each, plus 5, plus 5, plus 5, plus 5 and plus 5. Right? A charge of -5 is placed at a distance d from O. Right? -5 is placed at a distance d from O. Another charge can be brought from infinity to point O. Right? Infinity to point O without doing any work. Right? That's a good hint. We know delta W is given by Q delta V. No? If delta W is 0, right, from the other side, delta V must be 0. Delta V must be 0. Right? we know delta V is final minus initial. Then final minus initial is infinity. Then delta V is 0 and potential at infinity is also 0. Then Vf must be 0. Right? Then what's the point? The point is total potential at this system now is 0. Total potential at this system should be 0. Right? Because if potential difference is 0, right, potential at infinity is also 0, then in order to be that difference 0, potential at this system should be 0. Then write the potential and make it 0. Write the potential here and make it 0. We know potential is written as, right, 1 over 4 5 epsilon naught q over r. Then from plus 5, 5 over 5. Right? From the other 5, 5 over 1. From the other 5, 5 over 3. And minus 5 over d. Right? And v is 0. Right? Now this is given as 0. No? Then if this is 0, if you multiply also, that is 0, then 0 equals, right, multiply by 1 over 4 5 epsilon naught, that becomes 0, then divide by 5, right? Then what is remaining here is 1 over 5, right? 1 over 5, 1 second, right? 1 over 5 plus 5 plus 5 over, sorry, 5 cancels, no? Plus 1, right? Plus 1, 5 cancels, huh? Plus 1, and this is 1 over 3 minus 1 over d, right? Then take this 1 over d to this side, 1 over d equals, right, here common denominator is, right, we can have a common denominator as 15. 15 times, for 15, 5 times 3, and this is 15, and this is 5. Then 1 over d equals, right, 23, no? 23 over 15. We need d. D is 15 over 23. D is 15 over 23. It is 4. Right? It is 4. Right? So if you do something proper, right, the answer is slowly coming. It's gradually coming. Right? 46. 46. A straight composite rod is formed by joining two rods of equal lengths and equal cross-sectional area made from the different materials. The Young's moduli are y1 and y2. The equivalent Young's modulus of the composite rod is. Okay. Then let's say these two are the two rods connected together. Then the equivalent is here. Then if they are L and L, length of the equivalent should be 2L. Right? So we know in series combination, forces are equal. Then say this is F, this is also F for the equivalent, right? And extensions are different now, right? Forces are equal, but extensions are different. Then say extension of this one is E1 and extension of this one is E2. And their y's are y1 and y2 respectively, and equivalent y is, let's say, y, right? So when it comes to equivalence, always approach the question from the different quantity. Right? This is actually an equation we prove in the class, right? So if you can remember the equation of the equivalent, right, as 2y1 y2 or y1 plus y2, right? That's an easy pick. I'm explaining the proof here for all of you to know, and if there's anyone who didn't know this, then to you to understand, right? Then say this extension is E, then what we can say is E equals E1 plus E2, right? But from Young's modulus we know, see, Young's modulus, F over A equals Y times E over L. Then E can be written as, FL over YA, no? FL over YA. Then for here we can write E as FL over YA. Then apply it for each term separately. Then for the equivalent, same force F, but length is 2L, right? Y is YE, area is same A. For E1, same force, length is L, Y1A. And for E2, F, L, Y2, A. Right. Now, F2, F cancels, A2, A cancels, L2, L cancels. Then here 2 over YE remains. From here 1 over Y1 plus 1 over y2. Right? Then simplify 2 over ye equals common denominator here is y1, y2, and here that is y1 plus y2, y1 plus y2. Then subject ye, y is 2y1, y2 over y1 plus y2. Right? So answer is 3. That's a proved equation in the theories. That's a proved equation in the theories. Right? If you know the equation, take it at once. Right? So that's how you can take the advantage. Right? When you know these things. When you know these things from your memory. Right? If you can recall. 47. Two identical horizontal plates, each having an area 100, are placed parallel to each other with a separation of 4 centimeters. The space between them is filled with oil of viscosity coefficient 0.3. Right? Two plates, no? Two plates like this. Right? Okay. The lower plate is fixed while the horizontal force is applied to the upper plate. Right? While the horizontal force is applied to the upper plate. Then here a force is applied. Say this force is F. Right? Say this force is F. F. While a horizontal force is applied to the upper plate. If the velocity of the oil layers varies linearly across the gap, the constant horizontal force required to keep the middle layer moving is right. Now, if this plate is non-moving, right, velocity of the final liquid layer is also 0. Right, velocity of the final liquid layer is also 0 if there is non-moving. Then, if the plate above travels with, right, sorry, it says to keep the middle layer moving at 6. Okay, middle layer travels at 6. Then if middle layer travels at 6, if middle layer is at 6, right, it says it's varying linearly. Then gap from here to here is 6, no? Then there should be a gap of 6 again from here to here. Then this layer travels at a velocity 12. Right? That is a decision you have to make. Right? This layer travels at a velocity 12. This layer travels at velocity 6 is at 0. Then the constant horizontal force required to keep this moving. Okay, then we know from Newton's equation F equals eta A, right? Delta V over D. Newton's equation of viscosity, right? F is what we need. Eta is given 0.3. Then the area is 100 times 10 to the minus 4. 100 times 10 to the minus 4. Right? Delta V. Now what's the gap here? Separation 4 centimeters. This separation is 4 centimeters. Okay, then delta V of these two is 12 minus 0 is 12. And the separation is 4 centimeters, 4 times 10 to the minus 2. Right? So first of all, check the numbers here. Check the numbers here because different numbers are given. No? 3 is here as a number. Right? And 4 and 12 cancels. It is 3 again. 3 is here as a number. So as a number, what we are going to get is 9 only. Then obviously the answer is 0.9. Right? Obviously the answer is 0.9. Right? So I guess be smart in MCQs without doing the entire simplification. Then 48. 48. Two smooth concentric hollow cylinders of radii r and r plus x are fixed vertically. A smooth sphere of diameter d less than x rests at the bottom of the space between the cylinders. It is given an initial horizontal velocity u. As it moves, the normal reaction reverses direction when the position of vector makes an angle theta with the downward vertical. The initial velocity u is okay. Then let's consider this as my earth zero level. If that is earth zero level, at this point, now using this radius, we can write this height as r cos theta, no? Using the radius, and let's assume velocity of the object here as v, right? Velocity at this point of this particle is v, right? Then to get the velocity first, right? Apply energy. Say this point is A and this point is B. Then total energy at A equals total energy at B. Total energy at A equals total energy at B. Right? Total energy at A. No potential energy, but there's a kinetic half mu squared. Right? And at B, there's a potential energy mg. Total height from my zero level is r plus the above part r cos theta. Plus there's a kinetic energy also half m v squared. Right? There's a kinetic energy also half m v squared. Right? Then m is common, no? M cancels off. Right? Then multiply the entire equation by 2. Then this becomes u squared. Right? And here r is common. Then if r is taken out, 2gr 1 plus cos theta. And here v squared. Now for the future reference, let's keep v squared subjected. V squared equals u squared minus 2gr 1 plus cos theta. Right? Say this is equation 1. And now use f equals ma at this point, because now if it alters the sides, my argument is this: if it alters the sides, which means momentarily that reaction is going to be 0, right? Because initially this is in contact with the outer surface of the tube. Initially this is in contact with the outer surface when it is projected, and at one point, right, it is going to alter the sides. Then reaction from the outer surface becomes 0, no? Then at this point reaction is 0. At this point reaction becomes 0. Now other forces acting on the system are here mgx, right? And this reaction acts, and reaction is going to be 0. Reaction is going to be 0. Right? This reaction acts, but the thing is reaction is going to be 0. Now if we apply F equals ma towards center, see, F equals ma towards center. F equals ma towards center, right? F equals ma towards center, like this, right? Then towards center we have r plus mg. If this angle is 0, this is also 0, no? Then mg cos theta. Mg cos theta equals m v squared over r, right? mv squared over r, right? So this is r dash reaction, right? So we know when it alters, r dash becomes 0. When it alters, r dash becomes 0. Then it is mg cos theta equals mv squared over r, right? Then m2, m cancels. Then multiply this r here, gr cos theta equals v squared, no? V squared was initially proved here. U squared minus 2gr 1 plus cos theta. Right? Simplify. Then this is gr cos theta equals u squared minus 2gr minus 2gr cos theta. Right? Then if you take this is capital R, ne? This is capital R all the way from here. Right? This is capital R all the way from here. Capital R, right? Capital R. Okay, then here also capital R, capital R, capital R. Right, not simple R. That is given as capital R. That is given as capital R. Okay, then take this minus 2gr to this side, then it becomes 3gr cos theta. Right? Plus this one 2gr equals u squared. Then gr is common. U squared equals gr is common. Take it out. Then 2 plus 3 cos theta. Right? This is u squared. We need u. U is the square root of this. U is the square root of this. It is 1. Right? It is 1. Right? U squared is found. No? That's enough. U squared is found. Right? U squared then again. Then get you 49. 49. Figure A shows a ring of radius capital R and mass M. Figure B shows the same ring after two masses, each of mass M naught, located at mutually perpendicular positions OX and OY, have been removed. The gravitational field intensity created at the center O by the ring in figures A and B are given by. Right. Now, if there is a complete ring, right, this is an occasion, a popular occasion, we discussed in the theories also. Right, if there is a ring given, right, if there is a ring given, right, we don't have equations for rings in gravitational fields, right? Then what we do is we are splitting this into infinite number of or simple n number of very large number of, right, small charges, right, small charges. Now each and every charge is going to create forces here on this one at middle, right? Forces and gravitational fields actually, and they are exactly equal and opposite, no, right? Exactly equal and opposite, because this F is given by, we know, G m1 m2 over r squared, right? If masses are equal, distances are equal, right, then the forces are equal, then all are going to cancel each other, and this resultant is zero, right? Force becomes zero. When force is zero, gravitational acceleration is also zero, right? Gravitational intensity, gravitational field intensity is also zero, right? Now for the other case, right, for the other case, right, for the other case, now from this, two are removed, one mass from here and another mass from here are removed, right? Now when they are removed, now about G, they are asking, no, right? So you know this approved equation, G dash can be written as Gm over r squared, Gm over r squared, right? It can be written as Gm over r squared. Then when this side is removed, right, when this side is removed, right, this force, this is created with the particle at the exact opposite side, right? The force created by the particle at the exact opposite side remains, because no one to cancel this force, right? This is removed. And similarly, there's another force with the particle at this side, right? Attraction forces, no, gravitational fields, gravitational attractions, right? Like this, same magnitude in this direction, right? Same magnitude in this direction, right? Because of this, no one to cancel that. Then resultant of these two is going to be in between. Resultant of these two is going to be in between, right? And say G is G dash. Here also G is D dash, G dash. Right, now the resultant is asked. Right, we know this G dash equals G m naught. The mass is given as m naught, no, m naught over r squared. Right, then r is resultant is square root of G dash squared plus G dash squared. Right, always if you have identical perpendicular vectors, right, always if you have identical perpendicular vectors, resultant is always going to be root 2 times one vector, right? Resultant is always going to be root 2 times one vector if you have identical vectors, right? And this is root 2 times one vector G dash, then root 2, right, G dash is G m naught over r squared. Then in this direction, it is 2, no? 0, and here this is given, right? Then it is 2. It is 2, right? It is 2. Then 50th. 50th. As shown in the figure, an object is attached to a spring immersed in water. Within one time period, the variation of momentum P with displacement y measured from the equilibrium position is correctly represented by, assume that during the motion, the object does not emerge above the water surface and that initially the spring is maximally compressed. Oh, initially spring is maximally compressed. Consider vector quantities in the vertical upward direction as positive. Right, vector quantities in the upward direction as positive. Right. Then we have a popular graph we draw in simple harmonic motion, right, about velocity and distance displacement, no? Right, velocity and displacement, that's a popular graph we draw in simple harmonic motion, right? If there's no energy loss, right, if no energy loss, if no energy loss, right, we know what we are going to get is something like this if there's no energy loss, right? And these points are Vmax values, these points are Vmax values, actually minus Vmax this side, and this is A, and this side is minus A, right? This is what we get for velocity. For velocity, now momentum is mv, no? If mass is same, if mass is same, if mass is unchanged, then mv also has the same shape. But most importantly, in this question, there's a damping. Energy is lost. Right? There's a damping that is in water. The pendulum or the spring is in water, that is not in air. Water has a damping. then it is going to damp. It is going to damp at this point, right? It is going to damp at the point. Going to damp, right? So when it damps, what happens is, when it damps, that's a damping now. That's a damping. We call they are damping oscillations. That's a damping oscillation, right? Then when it damps, what happens is energy of a simple harmonic motion is given by half k squared, no total energy, half k squared, right? Which means energy is proportional to a squared, right? In the damping, when energy decreases, right, amplitude also decreases. In the damping, when energy decreases, amplitude also decreases. When energy decreases, amplitude also decreases. Then amplitude should decrease, and at the same time, when energy decreases, right, what else? Velocity also decreases, right? So based on these two, right, we can select one easily, right? Now, if you go to the first one, right, amplitude is decreased, we can see amplitude is decreased, but see, velocity of the first phase is less than velocity of the second phase cannot be. Velocity should also be decreased, right? Velocity should also be decreased, right? And in the second one, it's equal, right? And the third one amplitude has increased, cannot be. Initial amplitude has been this and final amplitude has been this, right? Increase whenever. Then fourth one, initial amplitude is here, final amplitude is here, decreased. Initial velocity is here, final velocity is here, decreased, correct. Then 4 is correct, right? 4 is correct. 4 is correct, right? So likewise, right? If you know these theories, when you know these theory parts properly, right, easily we could do, right? So then we have come to the end of all 50 MCQs about this Western Provincial paper, right? Western Provincial paper. Any questions? Any questions? Any questions? Anything to know? Or is it clear enough? Is everything clear? Now, with the things I have, with the, I mean, hectic schedule I have these days, now this is the time that I could take this, right? Sorry about it, right? Otherwise, usually I prefer 7, 8, somewhere around, but now with the schedule, now I had to start this at 11, right? All right. No questions. Then, if no questions, we can wind up, right? If no questions, right, we can wind up, right? If you don't have any questions, right, then if no questions, right, we are good to wind up, right? Then yes, now we have finished the all 50 MCQs of the Western Provincial paper, right? We have finished all 50 MCQs of the Western Provincial paper, and there are other provincial papers as well, right? I'll be taking them also to the discussion, right? And try all the types of questions, support seminars, provincial papers, especially before you go to the exam, right? And other than that, most importantly, the past papers, right? So try and familiar with these question types, right? Make yourself familiar with the question types. Then you won't get any new types of questions at the exam in that regard, right? Because higher the number of question types you know, higher the comfortability, higher the confidence you gain, higher the comfortability you have about the subject, right? Always higher the number of questions we practice, higher the comfortability we gain towards that, right? So that's the total point here. That's the whole point here. That's the whole point. Then practice more and more questions, right? And sit for the exam. Now we are like 16 days from the exam now. And about the other discussions coming up, you can get all the updates through the WhatsApp and Telegram channels, right? Then if no questions, we can wind up. Then stay safe and work hard. See you in the next session, right? Then good night and goodbye. See you.